Okay, yeah, let's see. I'm doing the recording now. Hmm. Okay, hi. So we will continue our lectures, but like I said, I will be using, I'm going to record this. We will not be having live lectures for some time, at least until I get back to the office. So I want to cover some topics in this mode, and then I will upload it, like I said, and then you can have a look at it and listen to it whenever you get time, and you let me know in case you have any questions. Please contact me on Slack or send me an email, or you can even call me. But I hope to come back to office soon once the campus lockdown is over. Okay. So we've been writing several types of programs in the last several lectures, and we kind of did object-oriented programming. We had a glimpse of what is object-oriented programming, and I shared some code examples. We might touch upon them maybe later during a future lecture, but right now in this particular lecture I would like to talk about generally about programming solutions to problems, and in particular I want to focus on efficiency. So generally when you try to solve something programmatically, we definitely want the program to be correct. We want correctness. Okay, so that is up to you. I mean, as a programmer, you are supposed to deliver a solution which is correct. Correct in the sense it should be generic. That means it should work for various types of inputs. So only if you write a program which will work for any kind of input and give the correct answer for all the valid inputs, only then you can kind of say that your program is correct. Okay, so in some ways, in some cases, you can actually prove it mathematically that the program, there is some condition in the program which will converge to a solution, or there is some condition which will get satisfied, which will lead to the solution. So for those kind of formalisms, you must actually do a course on algorithms. So if you are interested in that, you can do that. There are several courses being offered here at IIT Mandi, but they are mostly PG level courses or in the higher semesters. So at this point of time, since this is your first programming course, we are generally talking about correctness. So in as much as possible, we will try to give various types of inputs to your program to see if it is giving you the expected output. Okay, and of course for this we kind of should know what is the correct output, but there could be some situations when you don't know what is the correct output. Okay, so we will not worry about those things right now. So we will assume that the programs which we write are in some sense correct. So correctness is a different topic. We will not worry about correctness now. In this lecture we will talk about efficiency. So not only is writing correct code important, but you should also write efficient code, because a program which takes too much time to compute, especially when there is a better program can be written for the same problem, then obviously the program which takes too much time is of no use. We will see that example soon in later in this lecture. Okay. So in this talk we will try to somehow quantify what we mean by efficiency of programs. So given two solutions to the same problem, that means two programs solving the same problem, how can we say that one is more efficient than the other? So that is broadly what we are trying to answer. So most of these slides I have taken from the IC250 in 2018. Okay, but because many of the ideas are directly carry forward. So let's see. So just like how you design houses or whatever it is, no? I mean, when you want to design something, you need to spend some time planning it. So the same holds for programs, especially when you're writing large programs or programs which are mission critical. You might want to spend some time on trying to design the right program, and in many cases that design is based on choices. You need to choose the right data structure, and you need to choose the right algorithm. So you have seen various data structures over the past several lectures. We have seen data structures like lists, we have seen dictionaries, we have seen tuples, we have seen NumPy arrays. So there are various types of data structures which are available to you as a programmer, available in Python in particular. So based on the type of problem you are trying to solve, you might need to use an appropriate data structure. And also when you study algorithms, you will also realize that some problems can be solved more efficiently by using certain data structures. In addition to data structures, you should also choose the right algorithm. So like I said, the study of algorithms itself is a separate topic by itself, but generally there are various algorithm design paradigms like greedy algorithms, dynamic programming algorithms, divide and conquer algorithms. So that really depends on what is the type of task and what are the types of constraints which you have in which you are trying to solve the problem. So there are techniques to look at algorithms, and the various algorithm paradigms are there, and there are also techniques to look at various data structures. And based on what is it that you're trying to achieve, you must choose an intelligent data structure and an intelligent algorithm so that your program is reasonably efficient. So that is one constraint. The second aspect which you must look at is how are you going to implement it. So for example, in this course we are dealing with Python, but there could be situations where you might need to use a different language, a different programming language. For example, C, for example, is a language which is probably more efficient than Python because it is a compiled language. Perl is in some sense similar to Python. Perl is another language. It is popular in some communities, but these days Python has become very popular. Although there are a lot of people who still program in Perl. So different implementations will have different efficiencies. So should our definition of efficiency depend on how we implement the program? So that is a question which we want to answer. Okay. So ideally, when we design a program or design an algorithm to solve a particular problem, the efficiency of that algorithm must not depend on how you implement it, on what language you implement, because languages keep changing. What is there today may not be there tomorrow, but the algorithm which you design, we would like the algorithm to remain independent of the program, and you must be able to say which algorithm is better. I mean, that one algorithm is better than some other algorithm, irrespective of how you implement it. That is what we must be able to say. Another thing is, of course, the hardware and the operating system on which the program is running. The speed of computers keep changing. There could be faster and faster processors, 1 gigahertz, 2.8 gigahertz, or whatever it is now. And there could be different operating systems, right? Some operating systems are inherently faster. For example, Linux or Windows running on a desktop is usually more powerful than Linux running on a Raspberry Pi. Right? Raspberry Pi is a small handheld, like a credit card size computer, which is very, very small, which is meant for low power applications. And of course, finally, we also depends on the data. Some data sets are big, so like for example, sometimes there are only 10 records, or there may be only 10 or 100 or 100,000 data points, but sometimes you might have millions of data points. So your algorithm, your definition of efficiency must scale according to what is the type of data which you have, according to the size of the data. So now the question is, how do you decide what is the best algorithm for that particular problem, or how best is probably a little strong word here, maybe we should say better. How do you say that one algorithm is better than another? So that is done by defining some basic operations. Let's say, for example, operations like comparison, arithmetic operations, copying, etc. of scalar variables. We will count all of them as one unit. Okay, so this assumption is that, okay, so let me repeat what I said. So we are going to decide some fundamental basic operations, and then we are going to give because each time the computer is doing some operation, we are going to say that the computer is doing some x amount of work. Okay, x here is 1. So we are going to say that comparison, arithmetic, copying of scalar variables. Scalar variables means variables like integers, x, y, etc. Right, are all count as 1 unit. All of them count as 1 unit. So now this assumption is probably not a very valid assumption, but we are using this assumption to simplify our analysis. For example, now I am saying that arithmetic operations are counting as 1 unit of work which is being done. So for example, when you do x plus y and x multiplied by y, where x and y are integer values, the multiplication operation is probably requires more work than x plus y, right? So actually this assumption is not really valid, but to make our analysis simple, we will assume that all arithmetic operations, comparison operations, that is if a greater than b, no, that kind of comparison operations, arithmetic operations, etc., copying operations, that is if you want to do x is equal to y, you want to assign the value of y to x. Now those kind of copy operations, whenever scalar variables are present, we are going to count all of them as 1 unit. So it is important that we are talking about scalar variables. Okay, we are not talking about composite data types like lists or dictionaries. We are talking about simple scalar variables. So this is the assumption. Like I said, it is probably not a very valid assumption, but we are going to keep this assumption to simplify our analysis. So now let us find the average of n numbers. So this is the code which does this, and here we have quantified the amount of work which is being done. Okay, so now the code initializes sum is equal to 0 for I is 1 to capital N. N is the number of elements. Sum is equal to sum plus a is some array and I is my index. A is some array and I is my index, and I am keeping on adding it to sum. I am incrementing the value of sum with these values of AIs, and then finally average is equal to sum by n. So this is the program. So by going by my definition of the cost involved in these basic operations, this is an assignment, so it is like a copy, so it takes 1 unit of work. For I, now coming to this for loop, so in a for loop, what are the operations which happen? In this for loop itself, there are 2 things which happen. One, when you have a for loop like this, it is comparing the value of I to n, so there is a comparison happening, and there is also an increment happening. If the I is still less than n, then I is equal to I plus 1. That is automatically done inside the for loop. So actually this particular step here basically does 2 operations, a comparison and an increment, and this loop is done n times. So we do those 2 operations n times, that is the comparison and increment. So that is why this is 2n. The work for this particular code or this particular line is 2n, and inside that we are doing an arithmetic operation, and that is done n times because this loop iterates n times. So that is 1 into n. Then after the loop is over, then we do average is equal to sum by n, which again takes 1 unit of work, because we are going to assume that all arithmetic operations take 1 unit of work. So the total amount of work for this program, we can write it as 1 plus 1 plus 2n plus 1n, which is 3n, 2 plus 3n, where n is the size of my input. So basically we have now found out and a method, or we have kind of quantified the efficiency or the amount of work this program takes in terms of the number of inputs. Fine. So this is 2 plus 3n. This simple program takes 2 plus 3n units of work, where n is the size of the input. So that means it is linear in the size of n. For example, what it means is, if you want to compute the average of 10 numbers versus the average of 100 numbers, you can roughly think that computing the average of 100 numbers will take 10 times more than computing the average of 10 numbers, right? Because that relationship is linear. It is linear in the number of elements. So we have actually abstracted the problem. Like what this assumption here is, we have kind of simplified it. So now let's take a more complicated example. Suppose we want to find the average of numbers read so far. Okay. So now for this I have a function here. So this is my code. So this is my main program. Here we are assuming that the input is already there in the array A. Okay, there is some list which is already pre-populated with the inputs, and so this is my A. So first I'm going to find the average of this, then I'm going to find the average of this 1 and 2, then the average of 1, 2 and 3, and so on. So that is how I'm finding the average. I mean, so yeah, so let me write it better here. So this is my input. So first I want to find the average of this number, then I want to find the average of these two numbers, then I want to find the average of these three numbers, and so on. So this is the operation which I'm doing here. Right? Now, so let me rub that off because it is not needed. Fine. So this is my main program, which iterates through my input. There are the size of A is n. There are n elements in the array, so I goes from 1 to n. Then I have a function called getAverage. It takes A as an argument and it takes I as an argument, which gives me the current index. So that means I should find the average from 1 to the current index, that is from 1 to I, not n, 1 to I. And I am calling this n times. Fine. So this is the function here. It takes this I now becomes k. K is taken as the argument, and then this function is basically same as what we did here. Okay. So it does the loop goes from 1 to k, because k is now the current input, the current length, because I want to find that length will increment at every iteration. Incrementally, I want to find the average. So this function, we already know that this took 2 plus 3 n here from the previous analysis which we did. So here in this case, my n here is k, because there are k, we want to find the average of the first k elements. So this becomes 2 plus 3k. This comes from the previous analysis. We are replacing n by k. Then what is remaining is the main program for loop. So there are 2 units of work here, because there is an increment and a comparison, and this one is 2 plus 3k, right? This function is called n times. This function, because this loop goes from 1 to n, and this function is called 2 plus 3k times. So 2 plus 3k is called n times, correct? And so if you do the total, this will give me 4 plus 3k. 2 plus 3k, which will give me 4 plus 3k. Fine. And so this is done n times. So if you expand it out, basically what will happen is in the first time k is equal to 1. That means we are finding out the average of the first element. So that will take 4 plus 3. So if you substitute k is equal to 1, I will get 4 plus 3. K is 1 here. So 4 plus 3. It takes 4 plus 3 units of work to find out the average of the first 1 elements. It takes 4 plus 3 into 2 units of work to find the average of the first 2 elements. It takes 4 plus 3 into 3 to find the average of the first 3 elements, and so on. Fine. So you can just work it out yourself, so it will come straight. And then if you expand this, and so finally in the end, what we are doing, we will have to find out the average of all the n elements, which will be 4 plus 3 into n. Fine. So it is just that this is called so many number of times. That so from this analysis comes from that. So if you just expand this out, you will get this expression. So I've done the derivation here. You can have a look at it and confirm that it is correct. And so this kind of an operation takes a total unit of 5.5 n plus 1.5 n square. This is the where n is the size of the input. So basically, if you want to find incremental average, it takes 1.5 n square plus 5.5 n units of work, where the size of the input is n. So contrast this with this. Okay, see, these two programs are two different programs. This is a more complex program than this, because the purpose of this program is different. So it takes more work to do this program. So let's see some examples. So for example, if you do analysis like this on various types of programs, for example, one analysis time could be T1 of n, it could be 3 plus 4n. So n here is always the size of the input, and T1 of n here basically means the amount of units of work done, or in other words, the amount of time taken. So if you have to do more work, you have to spend more time. So one algorithm could take T1 of n, which is 3 plus 4n. These are various examples I am giving you. T2 of n, for example, could be 10 plus 4n. There could be so for this algorithm, for example, there could be more steps in the beginning followed by a loop. For example, in this algorithm, for example, there could be less number of steps in the beginning followed by a loop. So in some sense, this program requires you to do more work than this program. But the main point here is that if the n is large enough, both 3 plus 4n and 10 plus 4n will approximately be the same amount of work. It does not matter whether it is 3 plus 4n or whether it is 10 plus 4n for some particular large enough value of n. That we will see in a minute. Okay, that I'll show you right here. So for example, 10 plus 4n and 3 plus 4n. So you can see that there is slight, of course, the 10 plus 4n will be more than 3 plus 4n, but as the number of input, so in this graph, the x-axis is the size of the input, which is n, y-axis is t, which is the time taken or the running time, or in other words, the work done. So for example, the growth of these two functions, 10 plus 4n and 3 plus 4n, is approximately the same. There is a small constant difference, but that for large enough values of n, that difference is immaterial. Okay, so we'll see what it means when we come to the next type of programs. For example, now let's take another program which takes T3 of n, where 1 plus n plus 2n square. So this in some sense is similar to the size which we have here. This is 5.5 n plus 1.5 n square. So there is an n square factor here and an n factor here. That is also what is coming here. There is an n square factor here and an n factor here. So this program takes much more time. This program takes time in the order of square of the input. Okay, now suppose there is some more pre-processing, so some more processing you do in the beginning, and you have another program T4 of n, which is 10 plus 20n plus 2n square. Now this program or this polynomial is basically going to be larger than this polynomial, but for some value of n, some large enough value of n, both of them will be approximately the same. There won't be much difference. The difference will only be a constant factor. Now for example, if you consider, let's say you take 10 plus 4n and 1 plus n plus 2n square. Now here, suppose there is to solve a particular problem, suppose there is a program which takes 10 plus 4n time versus another program which also solves the same problem, but this one takes 1 plus n plus 2n square. Which one is better? So here you should see the relative rate of growth of both these functions. So that is plotted here, for example. So this plots a square polynomial versus a linear polynomial of degree 2 versus a polynomial of degree 1. So you can see that as n goes sufficiently large, this one the square term has a higher rate of growth than the linear term. So that means a program which has linear efficiency will take less amount of time to solve that particular problem as compared to a program which takes squared efficiency, which takes squared order of time. So the rate of, so what is it that we want here? We want a program to be efficient. That means we want it to take less and less time as much as possible. So a program which has linear growth is more efficient than a program which has squared growth, because the linear will take less time for large input when compared to the squared program. The program which takes order of time of the order of square of the input will take more time than the program which takes time which is linear in the time of the input. That is what is shown in this graph. So you can see that in the beginning there could be some values for small values of n. Here you are saying that the linear program is taking more time than this quadratic program. That is fine. And the assumption is that for large enough values of n, the difference will start to matter. In the beginning, you might feel that the linear program is more time consuming. That is actually what is shown by the graph. But if your program has to be generic enough and it has to run on any size of input, then only you have to worry about this. If you know beforehand that your program is only going to take inputs of only less than 2, then maybe it is okay to go for the quadratic program. That is fine. But if you want a generic program which will work on any type of input or any size of input, then you have to make sure that your so in this case the linear program will be more efficient than the quadratic program, because it takes less time. It takes less running time than the quadratic program. Fine. So this is again an expansion of that. So again this is 200 plus 400n versus 1 plus n plus 2n square. So for many cases, for smaller values of n, this one has higher growth, but for large enough values of n, again the quadratic term will dominate. So essentially this is a question of about which function is dominating the other. That is how we are measuring efficiency. So that is what is pictorially shown here. So 1 plus n plus 2n square versus 200 plus 400n. So you can see that the linear is till input size of about 200, the linear takes actually more time than the quadratic. But once you exceed input size greater than 200, then you can see that the linear is much better than the quadratic, because quadratic just scales up much more. It just takes too much time. So this kind of analysis is that of the asymptomatic complexity, and is also known as the big O notation. So some of you who have already done programming might be familiar with it. So we say that order of n, we say when you write O of n here, we basically say it is the order of n, and this is order of n square. So basically we say that an order of n square dominates over order of n. That is what is shown here. The order of n square dominates over order of n, because for some, the formal definition is like this: there is some n naught such that t of y is greater than t of x for n greater than or equal to n naught. That means, so that is the example here. Here our n naught is 200, because beyond 200 the quadratic term is going to dominate the linear term. Fine. So so that is one way to formally measure the complexity of a particular program. We have to see how many units of work has to be done to execute the program for various sizes of input. Fine. So there is formal definition is there. You can look up an algorithms book for that, but basically you can do a simple shortcut is that it depends really on the degree of the polynomial you are looking at. For example, order of n is less than order of n square, which is less than order of n cube, which is less than order of 2 raised to n. So no matter whatever constants you have here, the final dominating term is the n. So n is less than n square. No matter whatever is the constants here, forget about the constant factors. A quick shortcut is to realize that the n square term will dominate over n for no matter what the corresponding constants are. Fine. So the order relationship is like this. The asymptomatic complexity is order of n is going to be less than order of n square, which is going to be which is less than order of n cube, and this is less than order of 2 raised to n. So this is exponential complexity. So some problems require you to have algorithms which have complexity which is exponential in the size of the input. So this is exponential. So these are very slow programs. Only for very small inputs can such programs work. So many searching techniques, for example, brute force searching, will have order of exponential complexity. So this is the thing to remember, right? And finally, of course, this is useful for initial design, so that you know that you are trying to come up with a program which is reasonably efficient. And to finally make it make the code really efficient in production, you need to do other techniques, like you might need to do tuning, or you might need to do profiling, or you might need to do other compiler optimizations, etc., etc. So that is in the final production stage. But in the initial design stage, it is always better to come up with an algorithm which has the least amount of asymptotic complexity which you can solve, which you can use. So there is no magic bullet here. It really depends on the complexity of the task. Okay, so some simple problems can be solved by order of n algorithms. Their more complicated problems will require you to might not have an order of n algorithm. You might need to have an order of n square algorithm, and so on. So as the difficulty of the problem becomes more and more, the complexity of the algorithm, or the work required to solve the problem, will also increase. Fine. So for example, now this is a slide from a picture from an algorithms textbook. This is basically showing you the amount of time taken for various complexities, and this is the size of the input. So a program or an algorithm which is order of n, that is, which takes order of n linear complexity for various sizes of input, you can see that it takes less than 1 second. Even when n is 10, n is 30, n is 1 million, it just takes less than 1 second, because this is the algorithm is a linear algorithm, and it has to let's say, for example, you are finding out doing some operation on an array of some size, and this is the size of the array. Okay. If the problem you are solving is a simple problem, it can have an order of n algorithm, which is a linear algorithm, and practically for various sizes of input, it basically almost makes no difference. It almost takes the same time. Another type of complexity which is higher than linear but less than n square is n log n. Many algorithms have n log n time complexity. So you can see that now, you can see as the size of the input increases, the time taken also increases. For example, for 1 million input, it takes 20 seconds. For 100,000 input, it takes 2 seconds, whereas the other input, it takes only 1 second. Now let's go into more higher complexity. For example, an algorithm which takes order of n square. Now you can see how much the time differs. Less than 1 second for all of this. Once the input becomes sufficiently large, it takes 2 minutes, 3 hours, even 12 days for 1 million size. Some algorithms are order of n cube, and now it starts to get little impractical. 18 minutes for size 1000, 12 days for 10,000, and even like 31,000 years for 1 million. So basically, if you have an algorithm which is of complexity order of n cube, you can forget about running it for inputs greater than 10,000. That's basically what it means. So if the algorithm which you come up with has a time complexity order of n cube, then beyond 10,000 it is not going to work. The size of the input it can handle is at most 10,000. It takes about 12 days. Even if you run it on supercomputer or a more powerful machine, this 12 days might become 8 days. But you still cannot run it on 1 million size input, because it will just take too much time. That is what this rate of growth is telling us, this rate of growth. So this is n square, n cube is going to be even like this, going to have an order of higher growth. Right? We can see some simple examples of linear time algorithms. Let's say you want to compute the maximum of n numbers, and this is the algorithm. So this will take order of n, because you have to go through each element at least once. So that is why this takes order of n. So roughly you can think of it as the number of loops you are trying to execute. If there is only one loop, it is order of n. Now when this is an order of n square algorithm, this is closest pair of points. So suppose you are given an xy plane and there are various points here. You want to find out which of them are the closest. So this is an algorithm to do that. It basically has two loops, and it is going to look at each point and going to find out the distance from each point to all the other points, and then repeat this for each of the other points. Okay, and find the minimum, and you're going to repeat this for each and every. First you do it for this, you find out the minimum from this to all the other points. Then you find out from this one to all the others, and so on. So that is why you have two loops. So this is an order of n square solution, because it has two loops and it has to look at all data points 2 times. Another problem which is order of n cube. So this is an algorithm. Basically you want to given n sets, each of which is a subset of 1 to n, is there some pair which are disjoint. For example, if your n is equal to 5, your sets have values 1, 2, 3, 4, 5, and so these are 3 example sets. You have to find out if there is any pair which is disjoint. So for example, here in this case 1, 2 and 3, 4, this set A, this set and this set are disjoint, whereas this set and this set are not disjoint. So suppose you are given many such sets, come up, whenever you find out a disjoint set, come out. That is what the program should do. So this solution which they have given here is an order of n cube solution. So basically what it is doing, it is going to iterate through every 2 sets. So for one particular set, it is for a set I is looking at the other set Sj. So it is taking one set, it is taking the other set. It is now going to compare each of these. It is going to compare 1, 3, it is going to compare 1, 4, 2, 3, 2, 4 to see if anything is common. Then it is doing it for all possible pairs. That is what this is doing here. So that is why you have 3 loops here, and so this is taking time order of n cube. So this program is not a very efficient program, because the size of the input now here was 5, n was equal to 5. The moment you give, so from this table, from this roughly we can see that an order of n cube algorithm beyond 1000, for example, it becomes hopelessly inefficient. Fine. So so this is an idea of how to determine efficiency of programs. So our coverage was very brief, and we just looked at it at a high level point of view. The main thing to remember is that that of asymptotic complexity and the big O notation, what we have said, this is the big O notation. And remember, whenever you work out the time taken for a particular algorithm based on how much amount of work each unit operation takes, once you come up with some polynomial which represents the amount of work, you can compare that polynomial with other polynomials by comparing it in the big O form. That means you look at only the term with the largest degree. So an order of n square algorithm takes more time than an order of n algorithm, because n square dominates n for sufficiently large value of n. Okay, so remember this graph, that there is some input n naught beyond which the order of n square algorithm will dominate over the order of n algorithm. Okay, thank you, and I hope you can go through the slides once again, and for more advanced analysis on this, you can look at some textbook on algorithms. Okay. Thank you.